This is Module 1, Video 5, More Inverse Laplace Transform Techniques, EE300, Fall 2016. In this video, we'll review the highlights of the previous video, discuss the nuances of dealing with complex conjugate poles, examine how to handle multiple order poles, and we'll see how to deal with improper rational functions. We'll look at what to do with e to the minus st terms, we'll summarize what's in this video, and we'll look ahead to what's in the next video. Review of previous video. In the previous video, we stated that the Laplace transform is unique for our intents and purposes, so given a Laplace transform, we should be able to determine the waveform that it came from. We showed that when a waveform was a weighted sum of n exponentials, each with a different rate, then the Laplace transform had the form of a proper rational function, where a rational function is just a ratio of polynomials, and where a proper rational function has a numerator whose order is strictly less than that of the denominator. When the Laplace transform is a proper rational function and has n distinct roots, we saw we could write the Laplace transform in a partial fraction expansion. We showed how to find the residue of each partial fraction term using the cover-up method. We could go back to the time domain from the Laplace frequency domain by term inverse transforming each partial fraction to recover a weighted sum of exponentials with distinct rates. Here's an example of the cover-up method. Given this Laplace transform, what's the corresponding time domain waveform? The given f of s has a numerator that's second order and a denominator that's third order, so f of s is a proper rational function. The order of the numerator is strictly less than the order of the denominator. You know how we'll factor the denominator. You should know how to use your calculator to find the roots of polynomials. We'll show later how to use MATLAB to factor polynomials. Before factoring, we want to make sure that the leading coefficient of the denominator polynomial is 1. We write our partial fractions in the form something over s plus 1 plus something over s plus 2 plus something over s plus 3. We start by finding the weight of the s plus 1 term, the residue of f of s at s equals minus 1. We cover up s plus 1 in the denominator and evaluate what's left at s equals minus 1, the value that makes s plus 1 vanish. What's left is an arithmetic expression that evaluates to 3. We put the 3 in the weight of the 1 over s plus 1 term in the partial fraction expansion. Next, we repeat the process for the pole at minus 2. We cover up the s plus 2 and evaluate at s equals minus 2. Again, we're left with some arithmetic, and this time evaluating to minus 2. We make that the weight of the 1 over s plus 2 term in the partial fraction expansion. We do the same operations for the third pole at s equals minus 3, find the residue at minus 3, cover up s plus 3, evaluate at s equals minus 3, and this time we're left with 1. We put that into the partial fraction expansion. We check what we did before we do the inverse transform. In this case, if we multiply everything out, the leading coefficient of the numerator should be 2, and 3 plus 1 minus 2 is actually equal to 2, so it checks. We can now inverse transform term by term to obtain the result that f of t was 3 e to the minus t minus 2 e to the minus 2t plus 3 e to the minus 3t for t greater than or equal to 0. Complex conjugate poles. When we developed the Laplace transform and its properties, we found the Laplace transform of cosine and sine by building them out of a constant amplitude complex exponentials. Since cos beta t is the real part of e to the j beta t, it is 1/2 the sum of e to the j beta t and its conjugate. Since sine beta t is the imaginary part of e to the j beta t, it is the difference of e to the j beta t and e to the minus j beta t divided by 2j. When we find the Laplace transform of cosine and sine by transforming the individual terms, we see that both transforms have the same poles, but the residue at those poles is different. In particular, we can see that 1/2 is the residue of the Laplace transform of cos beta t at s equals j beta, and that the real amplitude of cos beta t is twice the real residue value. For sine, the residue at j beta is minus j over 2, and the amplitude is twice the negative of the imaginary part of the residue. What happens if we add sine and cosine? Consider a waveform that is the sum of a cosine and sine of the same frequency with amplitudes A and B respectively. We can express the Laplace transform of our waveforms by superposing either the forms with quadratic denominators, where the coefficients of the first order numerator are real, telling us that the sum of a cosine and sine of the same frequency has a real valued 0 at s equals minus b beta over a, or we can express cap f of s in terms of its residue at plus and minus j beta. When expressed in terms of the residue at j beta will be the sum of the residue from the cosine term and the sine term, and similarly for the residue at minus j beta. For real valued f of t, the residue at j beta and minus j beta will always come in conjugate pairs. If we call the residue at j beta the pole with a positive imaginary part k, then the residue at minus j beta is k conjugate. Our cosine amplitude A is then twice the real part of the residue at j beta, and our sine amplitude B is the negative of twice the imaginary part of the residue at j beta. We can write f of t in terms of the residue at j beta as twice the real part of k times cos beta t minus twice the imaginary part of k times sine beta t. We know from trig that we can also write this f of t in magnitude and angle form as a cosine of magnitude c greater than or equal to 0 with angle theta, where c is the square root of a squared plus b squared, and theta is the inverse tangent of b over a, negative inverse tangent of b over a. We can then recover a and b from c and theta through a equals c cos theta and b equals minus c sine theta. Even if expressed differently, this is the same waveform, so it has the same residue. So we can the residue can be expressed in terms of c and theta as c over 2 times e to the j theta. That's the residue at j beta. In terms of the magnitude of and angle of the complex residue k at s equals j beta, our waveform is twice the magnitude of k times the cosine of beta t plus the angle of k. Things work the same when our waveform is a sinusoid with an exponential envelope. We write the waveform in either cosine plus sine or magnitude and angle form. By the multiplication by e to the minus alpha t at property, the poles of the constant amplitude sinusoid at plus minus j beta are shifted to s equals minus alpha plus j beta. For a real valued waveform, these poles will always come in complex conjugate pairs. The residue of the Laplace transform at the complex conjugate poles will also come in complex conjugate pairs. Again, letting k stand for the residue of the pole with the positive imaginary part, we can write cap f of s in terms of its residue. We recover our time domain waveform from the residue in exactly the same manner except as we did with the constant amplitude case, except we now include the exponential envelope term at e to the minus alpha t. Let's work an example where the Laplace transform of a waveform has complex poles and complex residue. Here's a cap f of s with a quadratic numerator and a cubic denominator, expressed both in polynomial form and in factored form. We see that the poles are at s equals minus 1 plus and minus j beta and at s equals minus 2. We'll discuss how to use MATLAB to factor polynomials later in class. You should also know how to use your calculator to find the roots of polynomials. As before, we equate the factored denominator form of cap f of s with cap f of s written in terms of its partial fractions. Even at this stage, we should see that the time domain waveform will have a sinusoidal term with an oscillation rate 1, with an exponential envelope with a decay rate of 1. These come from the complex conjugate poles, plus a decaying real-valued exponential with a decay rate of 2. We find the residue of the pole at minus 1 plus j the same as we did with real-valued poles. We cover up the factor of s plus 1 minus j in the denominator and evaluate what's left at s equals minus 1 plus j, the value that makes that term vanish. In the numerator, 1 plus j squared is minus 2j. Make sure you understand that. Minus 1 plus j is the same thing as the square root of 2 times e to the j 3 pi over 4. It's at 135 degrees from the real axis. Squaring root 2 gives us 2. Squaring e to the j 3 pi over 4 gives us e to the j 6 pi over 4, which is e to the j 3 pi over 2, which is minus j. Try to get comfortable with where complex numbers are in the complex plane. The real part of the denominator is minus 12 plus 12, which is 0, and the imaginary part is 4 times minus 2 plus 12, which is 4. In the denominator, we have 2j times 1 plus j. The 2j goes into the 4j 2 times, and we clear the 1 plus j from the denominator by multiplying by 1 in the form of the denominator conjugate over itself. Bottom line, the residue at minus 1 plus j is 1 minus j. We put this back into the partial fraction expansion above. The residue of the complex conjugate pole will be the complex conjugate of the residue we just found, so we can put that back in too. We still have to find the residue at s equals minus 2. Covering up the s plus 2 term and evaluating s equals minus 2, we have 16 minus 12 plus minus 24 plus 12, which is 4 in the numerator, and minus 1 and 1 minus j times minus 1. In the denominator, we have minus 1 minus j times minus 1 plus j, which is 2 in the denominator. So the residue at s equals minus 2 is 2. We put that into the partial fraction expansion. The residue of the pole at s equals minus 1 plus j is 1 minus j. If we express the sinusoidal component of the waveform in cosine plus sine form, then the amplitude of the cosine term will be twice the real part of the residue, and the amplitude of the sine term will be the negative of twice the imaginary part. Of course, we have to include the exponential envelope, decaying at 1 since the real part of the pole location is minus 1. The rate of oscillation of the cosine and sine are 1 because the imaginary part of the pole location is 1. We have to add in the exponential decaying at rate at 2 from the pole at minus 2, which has an amplitude of 2. We can also express the sinusoidal part in magnitude angle form, where the magnitude of the cosine is twice the magnitude of the residue, and the angle of the cosine is the angle of the residue. Again, that cosine has an exponential envelope at a rate of 1, and again we add in the exponential of amplitude 2, decaying at a rate 2. Multiple order poles. Previously, we have seen that higher order poles arise when waveforms get multiplied by the ramp. So the waveform of t itself has a double pole at the origin, and t squared has a triple pole. When we multiply e to the minus alpha t by a ramp, we go from a single pole at s equals minus alpha to a double pole at s equals minus alpha. What happens if we have sums of these kinds of waveforms? Suppose we add together a constant, a ramp, and an exponential. The constant has a pole at the origin, and the ramp has a double pole at the same place. The exponential has a pole at s equals minus alpha. When we combine these over a common denominator, we see that the Laplace transform has a double pole at the origin as well as the pole at minus alpha for the exponential. Even though the waveform included both a constant and a ramp, we wouldn't see that in the factored form where we just see the double pole at s equals 0. If we were to go back to the individual terms, we would have to be sure to include all powers of 1 over s. Let's also look at the sum of a constant, an exponential, and a ramped exponential at the same rate. Again, we transform each term individually, and we see the pole at the origin, the single pole at s equals minus alpha, and the double pole at s equals minus alpha. But when we put these all over a common denominator into factored form, we only see the pole at the origin and the double pole at s equals minus alpha. If we were to go back to the individual terms, we'd have to include all powers of 1 over s plus alpha. So when we were given a proper rational function with a pole of order r, we have to include all powers of the pole in our partial fraction expansion. For each of the n minus r ordinary poles, we will have our ordinary residue, but there will be r terms for the pole of order r from 1 over s minus p1 to 1 over s minus p1 to the rth power, each with its own coefficient. We only have one term to cover up in the factored expansion, so how do we find these extra weights? There's two basic ways to do this. One is to use the method of matching coefficients. The other turns the problem into a series of problems involving first-order roots. We'll look at matching coefficients first. In the matching coefficients approach, you write out the partial fraction expansion to include all the powers of the repeated pole. We use the cover-up method to find the weights of the poles that aren't repeated, including any complex conjugate pairs, and we use cover-up to find the weight of the highest power of the repeated root. Then we label the unknown coefficients, put everything over a common denominator, and then match the coefficients of powers of s in both numerators. Let's work an example. We write our partial fractions as the usual sum of terms, but this time, since we have a double pole at s equals minus 1, we include both something over s plus 1 and something over s plus 1 squared terms. We find the weights of the ordinary pole and the highest order pole by covering up. First, to find the weight of the 1 over s term, we cover up s in the denominator and then evaluate what's left at s equals 0, leaving us with 1. We put that as the weight of 1 over s in our partial fraction. Next, to find the weight of the highest power pole, we do the same thing as we do with the ordinary cover-up weight. We cover up s plus 1 squared and evaluate what's left at s equals minus 1, this time resulting in 3. We put that into the partial fraction expansion too. Now we have one term with an unknown weight. We label that weight with a variable. By the naming scheme we were using earlier, this would be k21 since it's the first of the powers of the second root, s equals minus 1. In general, you would label the weight of all the powers of the repeated pole except for the highest power. The next step is to put everything over a common denominator. In the original expression for cap f of s, the s squared term had a coefficient of 3. The term on the right, in our right-hand side of our expression, the coefficient of s squared will have a coefficient of 1 plus k sub 2, 1. So k sub 2, 1 must be 2 to make the coefficients match. If we had had an even higher order pole, there would have been as many matching equations for powers of s as there were unknown weights. We put the weight in the partial fraction expansion, and then now we can inverse transform on our usual term-by-term basis to obtain the waveform was f of t equals 1 plus 2 times e to the minus t plus 3 times t e to the minus t for t greater than or equal to 0. We can see the three waveforms and the resulting sum in the graph. Another way to deal with higher order poles is to factor out enough of the repeated pole such that what's left can be expressed through an ordinary partial fraction expansion. For the Laplace transform given, we would factor out a power of s plus 1 out of the denominator, then do partial fractions as usual. We write our partial fractions expansion with unknown weights. By cover up, the weight of the 1 over s term is 1, and by cover up, the weight of the 1 over s plus 1 term is 2. We then bring what we factored out of the denominator back in. The s times s plus 1 term gives us another expression suitable for partial fractions, and the 2 over s plus 1 squared term is fine as it is. Doing cover up again, this time on 1 over s times s plus 1, we find that the weight of 1 over s is 1, and the weight of 1 over s plus 1 is minus 1. That should be a 1 over s plus 1 in the slide. Now we can inverse transform term by term to find that f of t is 1 minus e to the minus t plus 2t e to the minus t for t greater than or equal to 0. Again, in the partial fraction, that should be 1 over s plus minus 1 over s plus 1 plus 2 over s plus 1 squared. The individual waveforms are shown on the graphs as well as the solid line, which is f of t. Improper rational functions. If we try to use this approach with the earlier Laplace transform, it would have had to deal with an improper rational function. When we factor out s plus 1 from the denominator, we are left with an improper rational function to expand. We can deal with this by using long division to write the improper rational function as a polynomial in s plus a proper rational function. Let's take s squared plus s into 3s squared plus 7s plus 1. S squared plus s goes into 3s squared plus 7s plus 1 3 times with a remainder of 4s plus 1. Next, we expand 4s plus 1 over s squared plus s into partial fractions. We write this as something over s plus something over s plus 1. By cover up, the weight of 1 over s is 1, and the weight of 1 over s plus 1 is 3. Now we bring the 1 over s plus 1 back into the denominator. The first term becomes 3 over s plus 1. The middle term becomes another proper rational function to do partial fractions on, and the last term is 3 over s plus 1 squared. Expanding the middle term in partial fractions, we use cover up to find that the weight of 1 over s is 1, and the weight of 1 over s plus 1 is minus 1. We can then combine the 1 over s plus 1 terms to get 2 over s plus 1. We now have the proper fraction expansion, including all powers of the repeated pole. This is the same expression we found previously, of course, and so is the inverse transform. So when we have an improper rational function where m, the order of the numerator, is as large or larger than n, the order of the denominator, we can use long division to write cap f of s as an n minus m order polynomial plus a proper rational function, the remainder of the long division. While this helps us out with certain multiple order pole problems now, it doesn't help us in general because we don't have the inverse transforms of 1, s, s squared, etc. We'll return to these after we discuss impulses later in the term. E to the minus st forms. We have seen previously how powers of e to the minus s showed up in expressions involving delayed waveforms. For example, here's a short pulse that ramps down linearly from 0 to 1 over 2 time units. To write the waveform in signals we know the Laplace transform of, we recognize the original signal, if allowed to continue beyond t equals 2, can be counteracted by another ramp of the opposite slope starting at t equals 2 that add to 0. The delayed term in our signal turns out to have an e to the minus 2s factor in the Laplace transform. It's delayed by 2 time units, so it has an e to the minus 2s factor. When we were given a Laplace transform with powers of e to the minus s in it, we have to connect the e to the minus st term with something we know the Laplace transform of. For this Laplace transform, we can distribute the 1 over s plus 10 into both terms in parentheses, where we can recognize the signal as a decaying exponential with a rate constant 10, less another decaying exponential with the same rate constant that starts 1/10 of a time unit later. We recognize the e to the minus 1 term as an amplitude. Inverse transforming term by term, the signal is e to the minus 10t less e to the minus 1 times e to the minus 10 quantity t minus 1/10, all times u of t minus 1/10. We know that the second term in the Laplace transform stands for something that is 0 before t equals 1/10. When we look at these signals graphed, it seems the delayed signal is just the negative of the e to the minus 10t waveform that starts at t equals 0. And when we add the two together, we can see indeed that the sum waveform is 0 for t greater than 1/10. That being the case, we can now write our function showing the cases where it has finite value and where it has 0 value. These shouldn't be here. We've already done this. To summarize, in this video, we looked at the forms of waveforms that generated Laplace transforms with complex conjugate pole pairs. The waveforms were sinusoids and sinusoids with exponential envelopes. We saw how to use the complex residue of the pole with a positive imaginary part to determine the amplitudes of the cosine and sine terms of the waveform in cosine-sine form and the magnitude and angle of the waveform in magnitude-angle form. We saw that when we had multiple order poles in the Laplace transform, the partial fraction expansion had to include all powers of the pole up to and including its highest power. We saw 2 ways of finding the partial fraction weights for multiple poles, the method of matching coefficients and the method of doing repeated ordinary partial fraction expansions. That second approach sometimes led us to improper rational functions. In those cases, we could use long division to express the improper rational function as a polynomial in S plus a proper rational function. Finally, we saw how to deal with Laplace transforms containing a power of e to the minus s. In the next video, we'll apply the Laplace transform to the solution of circuits described by differential equations. This has been video 5 of Module 1 in E300 for Fall 2016, More Inverse Laplace Transform Techniques.